hopefully, yes, that it's working. Great. I'm excited to talk to you a little bit about what we're doing in the quantum application space and how we're leveraging Runtime, which is our Qiskit product, software product for running on hardware. So I'm going to just start out by this statement, which is essentially that we leverage our partnerships to identify valuable problems. And we really do believe this is kind of at the core of everything that we do in the applications research and application software space, which is that we think that our collaborations with our partners bring us one step closer to quantum advantage. And our definition for quantum advantage is shown here. It's the stage at which we have a quantum computer that solves valuable problems cheaper, faster, or more accurately than quantum computing. So this really is at the core of everything that we do. And in addition to that, we have selected some very specific areas that we focus on in terms of the application research that we explore in IBM Quantum. They tend to fall into these three buckets, and we've arranged them by category. I know all sorts of people have different ways of viewing this. This is our view. And essentially, it falls into the three buckets of simulation of nature, mathematics and processing data with complex structure, and other, which includes search and optimization type of problems. So in the simulation of nature category, we have things along the lines of physics, chemistry examples, materials science examples. In mathematics and processing data with complex structure, that's where quantum machine learning lives, as well as factoring and ranking. So the reason why we selected these is because of the promise of the potential for speed up at some point in the future. So the first two cases in the simulation of nature and the processing data with complex structure, we have seen examples, at least on paper in a theoretical world, where we're talking about at least polynomial, super polynomial, potential for exponential speed up in certain instances. And so these tend to be the ones that we really do focus on. In the other category, where we're talking about search and optimization type of applications, for example, we expect that there's a quadratic speed up. We've seen, however, when we're working with partners, that there are a lot of incredibly valuable use cases in this area. And in addition to that, there are algorithms that we're exploring that belong to this space that could be potential accelerators for the other two areas. And so we have focuses across all three different areas. And it flashed through the quantum circuits. I think that something that I think is, at least visually, you can see it even without knowing anything about it, that they have different kind of characteristics for each of the different areas here. Some of the algorithms and circuits require higher depths, for example, in the simulation of nature. And so that helps us understand where we think on the time scale these types of applications will show first examples of quantum advantage. When we break these down into the different industry areas, the way that we've selected focus industries that map very well onto the simulation of nature, mathematics, processing, data, and complex structure, and search and optimization, you can see nearly an all-to-all connectivity here. And so effectively what we're saying is that there's a lot of very interesting use cases in aerospace and automotive, financial services, high-tech, energy, environment, and utilities, and healthcare and life sciences that have the potential for quantum advantage as defined by theory, or at least some sort of valuable speed up as defined by the industry. So these are some examples of the different areas. The list is, as you can imagine, and it can be endless. But we choose to focus in and hone in on very specific ones that we think have the most potential for quantum advantage. And so I want to just focus on one example that we recently spoke about. We have partnerships in this area, so the simulation of nature area in high tech, kind of coupling those two. We have partnerships specifically with NW ChemEx, QNASYS, and JSR, down good chemistry. And we actually spoke about this at our recent quantum summit that just happened in November. But I wanted to highlight this area as one example of a place where we're really working to develop out with partners the software that is needed to be able to run applications, and then making sure that there's an end user in the loop to help define what the problem is. And this is essentially what it looks like. So the Qiskit Runtime as a service is what we're developing. So we have these sampler and estimator primitives that are a part of Qiskit Runtime. And then when we partner with folks that are doing the integrations, what they're looking at is mainly the application model services, algorithm services, and things of that nature that rely and call on the estimator and sampler. And in addition to that, we are including in real time, as the science is being developed, the state of the art in terms of error mitigation, for example. And I'll talk a little bit more about what we're doing there. But this is the basic concept, and it's all about, at the end of the day, how do we best leverage our devices and the hardware on the back end. So we have several partners. These are a snapshot of some of our partners that are in the IBM Quantum Network who are working in the software space. And in some cases, we have direct collaborations with them. I show just one example here. Again, I would direct you to the video that we have on the summit to see some other examples that I mentioned earlier. But here's one that we have with QNASYS and JSR, where QNASYS is essentially integrating with Qiskit Runtime as a service, building on top of the primitives so that they can run an example use case that is of interest by JSR. So in this particular example, they're looking at MECP, which is minimum energy crossing point. It's a chemistry example to look at singlet and triplet states and the potential energy surface and where they overlap. So as you can see below, they're looking at it for CH2. So this is a really good example of what we're able to do with partnerships. The main, I think, benefit to using Qiskit Runtime as a service is that you can put in multiple circuits all at once. You don't have to break it up into piecemeal, but you can submit them all at the same time, and it'll run through the workflow for you. When it comes to the code, so this is what the code looks like for this particular example. And you'll see that there's an option line, and it says resilience level equals 1. So I'll talk a little bit more about what that actually means. This is the link that I was referring to for the YouTube video if you want to go look at the entire session and see more examples of integrations for applications in the chemistry space in particular with the partners that I mentioned. So very simple code, very easy to implement. And then in addition to that, we also announced some new improvements in error mitigation at the summit for runtime. And I'll talk a little bit about what's next there. So I think underlying all of this, simulation of nature is a promising space to build as a vertical for quantum computing applications, and we are partnering with folks to be able to build this out. Okay, so this is the essential concept of why we're looking at error mitigation. So this is again, it's sort of a conceptual drawing, but you can think of this as a graph where quantum circuit complexity is on the bottom and simulation cost or runtime is along the y-axis. If you look at the different curves, we have the classical computer curve, so looking at circuits as they increase in complexity goes up as an exponential. You'll see that the quantum error mitigation, error correction curve is essentially almost flat. It's a linear curve, and so you start with a very high simulation cost or overhead associated with it, but it remains relatively flat across the board as you go to increased circuit complexities. Quantum error mitigation, however, it also has an exponential. It's exponential in the number of qubits and the circuit depth. So it will vary very much based on that. And by the way, this is circuit dependent, so it'll vary a little bit case by case, but this is the general concept. And what we want to see and what we're trying to explore here is that error mitigation can actually get you to a noise-free regime that you can operate in a much earlier time frame than it would with exploring error correction. And so today we are here, and you can see the dot to the left side of the classical computer, so we haven't crossed that threshold yet. We want to get to the place where it sort of has that inflection point in the error mitigation curve. So there's a lot of different error mitigation techniques. By the way, these are all moving targets is another thing to keep in mind. So which error correcting code that we actually use in the future is still an open research question, as well as what we can do in the quantum error mitigation space. And so we think that as these continue to improve, that line for the error mitigation curve that's an exponential will continue to flatten out as well. So you can start seeing it really reduce the overhead and the simulation costs for increased circuit complexities as those methods continue to improve. But this is a snapshot of where we are today. And all of our applications research that we do, whether it's with external partners or internal, leverages error mitigation as a part of the research direction itself. There's another blog here, again, if you want more information on this particular concept and something that we've introduced as gamma, which is basically a way to evaluate how well a circuit runs on the hardware. I would encourage you to go to this website and check it out. So anyway, this is another thing to point out is that this will enable us to be able to run things today, right? And that, I think, is really key on the hardware and the devices that we have, even in the presence of noise. Okay, so recently, right, we just announced that we deliver error mitigation and sort of the optimizations that you need through the Qiskit runtime primitives. And so these are the two Qiskit runtime primitives that we leverage. One is the sampler, and the other is the estimator. And so these are very common needs that we've seen to be able to actually use as building blocks and, for example, to be able to integrate with the chemistry software. But these are essentially the primitives, and we've integrated the error mitigation into them. I wanted to show just one example. There are many. We have a ton of examples of these. Like I said, we use error mitigation in every single research paper that we put out recently, and so we'll oftentimes even combine different types of error mitigation as well. But this is one example that it shows and highlights the impact of error suppression. So they use dynamical decoupling in this instance to actually be able to map onto what would be the expected performance for the system versus what you can see with the hardware with no error suppression at all. It looks, essentially, the curve is meaningless. So this is an example. As I mentioned, there are many, and it's all across the different areas in simulation of nature and mathematics and processing data with complex structure as well. So we really do use error mitigation, error suppression everywhere, and it can have really profound effects. So this is our interface that we're using for error mitigation in Qiskit runtime and in the primitives. And so what we're trying to introduce is a very simple resilience level. So you can have resilience level of 1, 2, or 3 effectively to help introduce this error mitigation and different techniques that are available. And we'll continue to incorporate more as they become available in real time. So as of right now, in the case of both the sampler and the estimator, so in the sampler case, we have model-based measurement error mitigation. In the estimator case, it's model-free measurement error mitigation. And because there's almost no real overhead associated with having these types of error mitigation, we include it by default essentially as resilience level 1. And so when you saw the code that Qnesis used, they had the resilience level 1. And so that really improved their results. It helps us get to the levels of accuracy that we need to do our research. So this is essentially readout error mitigation is in this sort of 1 resilience level. Resilience number 2, we start integrating now different types and combining different types of error mitigation together. And so this is zero noise extrapolation. I think many in the audience are probably familiar with it, but essentially what you're doing is looking at different pulse lengths and then extrapolating back out what it would be in a zero noise regime. And so we also refer to this as being Z&E. So in resilience level 2, you have your readout error mitigation, you also have Z&E, and so you can test this to see how well your results turn out when you have both of these error mitigation techniques combined. And then the last error mitigation technique that that we have implemented for resilience level 3 is probabilistic error cancellation. So this was some work that we recently put out this year. It appeared on Archive. I'll point out that the Z&E is slightly older, but we do expect as time continues and new techniques become available that we will start implementing them as well. So this is the highest level of resilience. You can think about, you'll choose based on how, what you want in terms of your time kind of balance and the needs that you have for accuracy and the particular problem that you're looking at. You'll probably pick 1, 2, or 3 resilience level. But in resilience level 3, this is where we include the PEC. So we have readout error mitigation, Z&E, and now PEC combined. All right. And again, this is just a very simple, you just change that top options line of code so you can switch it over to saying now options resilience level equals 3. All right. And with that, I always like to end on our development roadmap and just show what we've accomplished this year. So we just announced that we have successfully made Osprey, which is our 433 qubit device. The team is working hard on Condor, which is now our 1,000+ qubit device. So we're expecting to, that's going to be one of the first milestones we hit early next year. We just announced dynamic circuits as well. And as you can see, this next year, 2023, 2024, 2025, we're really starting to develop out these different quantum serverless layer that has things like the circuit knitting toolkit and toolbox, so different tools to really help push the research along that's needed for circuit knitting, circuit cutting, embedding, et cetera. So we can leverage those as a part of the circuit knitting toolkit. And then in addition to that, you can see that there's an error suppression and mitigation line here as well. So we'll continue to evolve what is available in Qiskit Runtime towards that end. And then also continue working with partners and internally on the applications, services, and the quantum software applications. And with that, I'm happy to answer any questions that you all have. I'm just going to leave this up here.
Okay, do we have any questions from the audience? If there's no questions, I'll ask one question.
Okay, sure.
I'm curious to see all of these computers laid out till even 2025 there with Kookaburra. Has work begun on those, or are they kind of like a placeholder for what will become?
So if you look at kind of the illustrations as you go from left to right, you can see that there's new sort of technology development that kind of build up to it. And so we have the layout will change, and then we have sort of the classical connections that we need to make. And so all of these things taken together as we continue to build up are going to eventually roll into Kookaburra. So we've laid out this roadmap. It's ambitious, but it's not impossible. And as we even went up to the 433 qubits, we're developing the technology that will eventually be used in some of the larger devices.